Good morning, students. Today we will have a recap on the topic that we have discussed yesterday in class, that is transmission of weakly stationary process through a LTI filter. So here we have a random process x of t. This is applied as input to the linear filter. So this is a linear time invariant filter. This filter has a response h of t, and we will get an output y of t. We will discuss about the characteristics of this random process y of t in this topic. So generally, an input to the filter, if the input is x of t and we have a h of t as impulse response, the output is generally represented as convolution of the impulse response and the input signal. So this is what we have done. So we can express the y of t as the convolution of h and x, that is integral infinity to minus infinity to plus infinity h of tau 1 into x of t minus tau 1 into d tau 1, where this tau 1 is the local time. Now we will discuss about two characteristics. First thing, we will calculate the mean of y of t, and second we will deal with autocorrelation of y of t. So let's start with mean. So generally we will take when we want to find the mean of a random process, simply we have to take expectation on that random process. So this is the concept. So now let us consider this to be equation number 1 and this to be equation number 2. So now substitute your equation number 1 in 2. So instead of y of t, you just simply use this one. So expectation of the full term, we will get it, right? And now h of tau 1 is nothing but, it doesn't deal with expectation. We will have expectation only for the random process. So the expectation E outside is simply moved for before the random process. And we know that expectation of x of t minus tau 1 can be represented as mu x of t minus tau 1. We have already discussed in the previous topic that for weakly stationary process, this mu x of t minus tau 1 is a constant. That means it can be simply represented as mu x. So in the next step, we are writing this one as mu x. Since it is independent of time, we are bringing it outside the integral formula. So mu x integral minus infinity to infinity h of tau 1 d tau 1. And now this term is nothing but the frequency response at 0. So that is said to be h of 0, that is the 0 frequency response of the system. So the interesting result is that the mean of the stochastic process y of t is nothing but, we have to multiply the mean of the input x of t and the 0 frequency response of the system. So if you have mu x and h of 0, you can multiply these two factors so that you will get the mean of the random process y. So this is all about mean. Next thing, second thing is we will have autocorrelation function. So autocorrelation function is nothing but, you have two values t and u, which represents the two values of the time at which your output process y of t is sampled. So if you want to calculate autocorrelation, have expectation of the product of the random process at two different times, that is y of t and y of u. This gives you the autocorrelation. So use your equation number 1 and substitute for y of t and substitute for y of u. Here you will use the term tau 1 and for y of u you will use tau 2. So this gives the equation. Now again we know that this expectation holds only for this random process x of t minus tau 1 and x of u minus tau 2. So in the next step, we can apply the integral. You can check it here in minus infinity to infinity h of tau 1 and integral minus infinity to infinity h of tau 2 into d22, that is represented here, and this expectation is brought to this terms. We are producting these two random process, x of t minus tau 1 and x of u minus tau 2, and we're using the expectation here. So now it is clear that this expectation can be written as mxx of t minus tau 1 comma u minus tau 2. And in the next step, we know that it is a weakly stationary process. So it depends only on the time difference between the two signals, right? So now the equation simplifies to Rxx of tau plus T1 minus T2. And the final result is that if you substitute tau is equal to 0, our equation simplifies to this. So this is the mean square value of the random process y of t. So this is an important result. From this result, we will discuss the today's topic, next topic. So this is nothing but power spectral density of a weakly stationary process. In the previous topic, that is transmission of your x of t to a filter, this topic deals with time domain process, right? So it is a time domain process, whereas this power spectral density is nothing but frequency domain analysis of your weakly stationary process. So we have the impulse response, that is h of t. So now this is represented as inverse Fourier transform, inverse Fourier transform of the frequency response of the filter. So where h of f, which means denotes the frequency response of the filter, we can write it like this. So h of tau 1 equal to, this is simply your mathematical formula. I hope you have studied inverse Fourier transform. So we have applied that expression, h of tau 1 equal to integral minus infinity to infinity h of f exponential of j 2 pi f tau 1 into df. Now we already have an interesting result, that is our equation, the final equation of the previous topic. So this one, right? Now we are going to apply this h of tau 1 expression into that previous equation. For me it is 4.33. I hope for in class we have derived it and marked equation number 6, I think. So instead of h of tau 1, we are substituting this inverse Fourier transform equation now. Once this is done, again we are rearranging the integration. We are writing it in a df form first. So h integral minus infinity to plus infinity, h of f is here and this df is moved to the last. Simply we are rearranging, and the next integral is dealing with this one, tau d2. This is second one. So integral minus infinity to infinity d tau 2 and h of tau 2 is represented. And final thing is we want to write with d tau 1. So integral minus infinity to infinity this rxx rxx of t minus tau 1, and this all the terms that deals with tau 1 is written now, exponential of j 2 pi f tau 1 and this derivative dou tau 1. So simply we are rearranging the equations in terms of df is the outer integral and tau 2 is the second integral, and this is tau 1 integral. The last third one is deal with tau 1. So this seems to be very complex, right, this equation, but we can just simply replace this term, that is tau minus tau 1 as tau. So we are using that. So wherever you have tau 1, you can use tau is equal to tau 1 minus tau 2. It means that tau 1 equal to tau plus tau 2. So we are using this expressions in this previous equation and we end up with this equation now. So we have two exponential term now. Since we are substituting for tau 1, we have two expressions as exponentials. And now this is very clear, h of tau 2 exponential of j 2 pi f tau 2 into d tau 2. So you can refer your this equation, right? So we have this equation. So this is h of f is written here. So here it is complex conjugate h complex conjugate h asterisk of f now. So we know that h of f multiplied with h star of f, that can be denoted as magnitude of h of f the whole square. So we are now changing our expression as minus infinity to infinity h of f the whole square into this integral term. This remaining integral term comes as such here. So whatever inside the square bracket is now the Fourier transform of the random process x of t. So now this term is nothing but the power spectral density. We denote it as xx of f. So that is one done in the next step. So s xx of f is equal to integral minus infinity to infinity or xx of tau exponential of minus j 2 pi of tau d tau. So this is the power spectral density of the weakly stationary random process x of t. And now you can substitute this expression in this previous equation. So it is exponential of y of t square equal to integral minus infinity to infinity h of f square. Instead of this whole term, you can use s xxf into df. So this is the frequency domain equivalent of the time domain relation. So the mean square value of your linear LTI filter in response to a weakly stationary process is equal to integral over all frequencies of the power spectral density of the input process multiplied by the squared magnitude of your response of the filter. So this is the result. This is the final expression, and you have to conclude this topic with this statement. So your mean square value of the random process y of t is nothing but you have the power spectral density multiplied with squared magnitude of response of the filter over all integral over all the frequencies. So we have a topic called Wiener-Kirchner relations. This is nothing but this expression already what we have discussed here. So your xx of f equal to minus infinity to infinity or xx of tau exponential of minus j 2 pi f tau into d tau. This expression we are repeating the same, and from this we can calculate our rxx of tau also. So this is nothing but the same. You have to interchange your s and r, and your exponential term will have a positive sign here. So d tau is now df. So these two equations are known as Wiener-Kirchner relations. So this plays a fundamental role in your spectral analysis of a weakly stationary process.